All right, let's jump right in. Have you ever wondered how your phone can pull up a photo from 3 years ago in like half a second? Or how your social network keeps track of millions of people and all their connections? Well, the secret sauce behind all of that is something called a data structure. You can think of it as the invisible framework, the digital filing cabinet that secretly organizes our entire online world.
So I have to ask, what on earth could your social media feed and a clunky old filing cabinet possibly have in common? It sounds a little weird, I know, but the answer is surprisingly simple: organization. See, both of them are designed to do the exact same thing: store information so you can find it later. The only real difference is one uses manila folders and the other uses pure logic. And that logic, well, that's what we're going to demystify today.
And that really gets to the heart of it. A data structure isn't just a dumb container for data. It's all about storing it smartly. It's a very specific format for organizing all that information so that you can get to it and work with it as fast as possible. The key thing to remember is that it's all about defining the relationships between the individual pieces of data. Okay, so let's start with the basics, the most straightforward kind of organization out there: linear structures. And just like the name suggests, these are all about putting data in a sequence, one thing after another in a single straight line. These are truly the fundamental building blocks for pretty much all of programming. Right off the bat, we hit a fundamental trade-off in programming. On one side, you've got the array. Think of it like a brand new egg carton. You get 12 spots, all laid out at once. It's super fast to get to the 7th egg, but if you only ever store 5 eggs, well, the other 7 spots are just wasted space. The linked list, though, is more like a train. You can add a new car whenever and wherever you need it. It's way more flexible and you never waste space, but to get to the 50th car, you have to walk through the first 49 to get there. Now, let's take that simple sequence idea and add a little twist. Imagine a stack of plates at a buffet. When a clean plate comes out, it goes on top. And when you go to get food, you take that same plate right off the top. That's a stack. It follows one simple, crucial rule: last in, first out, or LIFO, as you'll hear it called. This is exactly how the undo button works in your text editor, by the way. And it all works with just 2 simple moves. When you add an item, you push it onto the top of the stack. Add another, and that becomes the new top. Then, when you want to take an item off, you pop the one that's currently on top. That's it. You can only ever touch that single top element. It sounds simple, but it is incredibly powerful. Okay, so now let's completely flip that logic on its head. This time, instead of a stack of plates, think about a line at a checkout counter. The first person who gets in that line is the first person who gets to check out. This is a queue, and its principle is, you guessed it, first in, first out, or FIFO. Your printer uses this exact logic to handle print jobs. The first document you send is the first one that prints out. The operations for a queue are just as clear-cut. New items get added to one end, called the rear. That's the NQ process. And when it's time for an item to be processed, it's taken from the opposite end, the front. That's called DQ. It's just a fair, orderly system, exactly like any line should be. Okay, so lines are great, but what happens when your data isn't a neat, straight line? I mean, think about it. What about a family tree, or a map of a subway system, or your gigantic network of friends online? For that kind of messy, interconnected data, we have to break out of the line and start using nonlinear structures. Probably the most common nonlinear structure you'll run into is the tree. It is absolutely perfect for representing any kind of hierarchy. Just think about the file system on your computer. You have a main C drive, that's the root. Inside that, you have folders, and inside those folders are, well, more folders and files. Each folder is a node, and everything inside it is considered its children. So a common question is, how is a tree different from something called a graph? It really comes down to 2 big things. A tree is a strict hierarchy. It always starts at a single root and branches out. And, this is key, you can never have loops or cycles. A family tree is the perfect analogy. But a graph is more like a social network or a city map. There's no single root person or starting point, and connections can go in any direction, forming these complex, interconnected webs. That ability to have cycles is what lets graphs model the real world so well. All right, so we've figured out some really clever ways to store our data. That's half the battle, for sure. But what good is a perfectly organized digital filing cabinet if it takes you forever to find what you're looking for? This is where searching and sorting become absolutely critical. Let's say you're looking for a name in a dictionary. A linear search is like starting at the very first word and reading every single one until you find it. It'll work, eventually,
But it's painfully slow. A binary search is what you actually do. You open the book to the middle. Is your word earlier or later in the alphabet? You instantly throw away the half you don't need and you do it again. It is incredibly fast, but it comes with one non-negotiable requirement. The data has to be sorted first. And that right there is the fundamental truth. Sorting isn't just about making a list look tidy. It's the essential prep work for efficiency. By arranging our data into a specific order, we unlock the ability to use these incredibly powerful, high-speed algorithms, like the binary search we just talked about. So how do programmers actually measure this stuff? Well, they plan for the worst-case scenario. This big O notation you see here basically describes how much slower an algorithm gets as you throw more data at it. That's the N. An O of n squared algorithm, written O of n squared, gets slow fast. But an O of n log n, O of n log n, scales beautifully. That's why merge sort is so reliable. It's always excellent. Quicksort is often faster, but you always have to watch out for that potential worst-case slowdown. And this chart really shows you why all that big O stuff matters so much. Look, when you've only got a handful of items, the difference is whatever. But as your data grows from hundreds to thousands to millions of items, that O of n squared algorithm becomes astronomically slower than the O of n log n one. This is literally the difference between an app that feels instantaneous and one that just freezes up. So we know sorting is great for finding things fast. But what if we could find data instantly? Like with no searching at all. This is where we get into the really cool stuff, what feels almost like magic: hashing. Hashing is a totally brilliant idea. Instead of searching for something, you take a key, like a username, and you run it through a special mathematical recipe called a hash function. That function instantly spits out the exact address, the exact storage location where that item is supposed to be. It's like a filing cabinet that tells you, go to drawer 117, without you ever having to read a single label. Now, this probably seems way too good to be true, right? There's got to be a catch. And you're right, there is. What happens if our magic recipe takes two totally different usernames, say John Doe and Jane Smith, and tells us to put them in the exact same spot? This is called a collision. It's when two different inputs accidentally produce the exact same output from the hash function. And in the world of computer science, this isn't some rare accident. It's a totally predictable problem that every good system absolutely must have a plan for. So the key is to have a strategy. There are two main ways to handle it. With open addressing, if a spot is already taken, you just look for the next empty one nearby. Simple enough. With chaining, each storage location is more like a bucket that can hold a list of items. So if John and Jane hash to the same spot, they just get tossed into the same bucket together. Problem solved. You know, when you boil it all down, it comes back to this one powerful idea. The choice of which data structure and which algorithm to use isn't some minor technical detail. It can literally be the difference between a program that feels snappy and one that might never actually finish running. It is the very architecture of performance. So I'll leave you with this final thought. The next time you're scrolling through a feed, using a search bar, or you hit that undo button, just take a second and think. Can you guess what's happening behind the screen? Is it a stack, a queue, a tree? Because now you know the language of how our entire digital world is put together.